Audiobook Science Class 8 Page 146 Chapter 12 Friction. You might have seen a driver of a car or a truck slowing down the vehicle at a traffic signal. You too slow down your bicycle whenever needed by applying brakes. Have you ever thought why a vehicle slows down when brakes are applied? Not only vehicles, any object moving over the surface of another object slows down when no external force is applied on it. Finally, it stops. Have you not seen a moving ball on the ground stopping after some time? Why do we slip when we step up on a banana peel? Figure 12.1. Why is it difficult to walk on a smooth and wet floor? Figure 12.1. In figure 12.1, we can see two boys. One boy steps on a banana peel and falls down. You will find the answers to such questions in this chapter. 12.1 Force of friction. Activity 12.1. Gently push a book on a table. Figure 12.2a. You observe that it stops after moving for some distance. Repeat this activity pushing the book from the opposite direction. Figure 12.2b. Does the book stop this time too? Can you think of an explanation? Can we say that a force must be acting on the book opposing its motion? This force is called the force of friction. Figure 12.2a-b. Friction opposes relative motion between the surfaces of the book and the table. Figure 12.2 has two images, A and B, which depict friction opposes relative motion between the surfaces of the book and the table. Page 147. You saw that if you apply the force along the left, friction acts along the right. If you apply the force along the right, the friction acts along the left direction. In both cases, the force opposes the motion of the book. The force of friction always opposes the applied force. In the above activity, the force of friction acts between the surface of the book and the surface of the table. Is the friction the same for all the surfaces? Does it depend on the smoothness of the surfaces? Let us find out. 12.2 Factors affecting friction. Activity 12.2. Tie a string around a brick. Pull the brick by a spring balance. Figure 12.3. You need to apply some force. Note down the reading on the spring balance when the brick just begins to move. It gives you a measure of the force of friction between the surface of the brick and the floor. Figure 12.3. In figure 12.3, a brick is being pulled by spring balance. Now, wrap a piece of polythene around the brick and repeat the activity. Do you observe any difference in the readings of the spring balance in the above two cases? What might be the reason for this difference? Repeat this activity by wrapping a piece of jute bag around the brick. What do you observe? Spring balance. Spring balance is a device used for measuring the force acting on an object. It consists of a coiled spring which gets stretched when a force is applied to it. Stretching of the spring is measured by a pointer moving on a graduated scale. The reading on the scale gives the magnitude of the force. Activity 12.3. Make an inclined plane on a smooth floor or on a table. You may use a wooden board supported by bricks or books. Figure 12.4a. Put a mark with a pen at any point A on the inclined plane. Now, let a pencil cell move down from this point. How far does it move on the table before coming to rest? Note down the distance. Page 148. Now, spread a piece of cloth over the table. Make sure that there are no wrinkles in the cloth. Try the activity again. Figure 12.4b. What we have just discussed is shown in figure 12.4. The pencil cell covers different distances on different surfaces. Repeat this activity by spreading a thin layer of sand over the table. Maintain the same slope throughout the activity. In which case is the distance covered the minimum? Why is the distance covered by the pencil cell different every time? Try to reason why. Discuss the result. Does the distance covered depend on the nature of the surface on which the cell moves? Could the smoothness of the surface of the cell also affect the distance travelled by it? Bojo says, I shall try the activity by wrapping a piece of sandpaper around the cell. Friction is caused by the irregularities on the two surfaces in contact. Even those surfaces which appear very smooth have a large number of minute irregularities on them. Figure 12.5. Irregularities on the two surfaces lock into one another. When we attempt to move any surface, we have to apply a force to overcome interlocking. On rough surfaces, there are a larger number of irregularities. So, the force of friction is greater if a rough surface is involved. Figure 12.5 shows surface irregularities. The first surface is of a book, which is rough. The second surface is of a table, which is comparatively quite smooth. Page 149. We see that the friction is caused by the interlocking of irregularities in the two surfaces. It is obvious that the force of friction will increase if the two surfaces are pressed harder. You can experience it by dragging a mat when nobody is sitting on it and when a person is sitting on it. Figure 12.6. You have to push on the box to keep it moving. Recall your experience when last time you moved a heavy box from one place to another. Figure 12.6. If you have no such experience, get that experience now. What is easier, to move the box from rest or to move it when it is already in motion? The force required to overcome friction at the instant an object starts moving from rest is a measure of static friction. On the other hand, the force required to keep the object moving with the same speed is a measure of sliding friction. When the box starts sliding, the contact points on its surface do not get enough time to lock into the contact points on the floor. So, the sliding friction is slightly smaller than the static friction and you find it somewhat easier to move the box already in motion than to get it started. 12.3. Friction. A necessary evil. Recall now some of your experiences. Is it easier to hold a kulhad, earthen pot, or a glass tumbler? Suppose the outer surface of the tumbler is greasy or has a thin layer of cooking oil on it. Would it become easier or more difficult to hold it? Just think, would it be possible to hold the glass at all if there is no friction? Recall also how difficult it is to move on a wet muddy track or wet marble floor. Can you imagine being able to walk at all if there were no friction? You could not write with pen or pencil if there were no friction. When your teacher is writing with chalk on the blackboard, its rough surface rubs off some chalk particles which stick to the blackboard. Figure 12.7. A nail is fixed in the wall due to friction. Page 150. Could it happen if there were no friction between the chalk and the board? If an object started moving, it would never stop if there were no friction. Had there been no friction between the tires of the automobiles and the road, they could not be started or stopped or turned to change the direction of motion. You could not fix a nail on the wall, figure 12.7, or tie a knot. Without friction, no building could be constructed. In figure 12.8, soles of shoes worn out due to friction. On the other hand, friction is an evil too. It wears out the materials whether they are screws, ball bearings or soles of shoes. Figure 12.8. You must have seen worn-out steps or foot-over bridges at railway stations. Friction can also produce heat. Vigorously rub your palms together for a few minutes. Figure 12.9. How do you feel? When you strike a matchstick against the rough surface, it catches fire. Figure 12.10. You might have observed that the jar of a mixer becomes hot when it is run for a few minutes. Figure 12.9. Rubbing of your palms makes you feel warm. You can cite various other examples in which friction produces heat. In fact, when a machine is operated, heat generated causes much wastage of energy. We shall discuss the ways of minimizing friction in the following section. Figure 12.10 depicts how striking a matchstick produces fire by friction. Page 151. 12.4. Increasing and reducing friction. As you have seen in the previous section, friction is desirable in some situations. Have you ever thought why the sole of your shoe is grooved? Figure 12.11a. It is done to provide the shoes better grip on the floor so that you can move safely. Similarly, the treaded tires of cars, trucks and bulldozers provide better grip with the ground. Figure 12.11a. Soles of shoes and b. Tires are treaded to increase friction. We deliberately increase friction by using brake pads in the brake system of bicycles and automobiles. When you are riding a bicycle, the brake pads do not touch the wheels, but when you press the brake lever, these pads arrest the motion of the rim due to friction. The wheel stops moving. You might have seen that kabaddi players rub their hands with soil for a better grip of their opponents. Gymnasts apply some coarse substance on their hands to increase friction for better grip. In some situations, however, friction is undesirable and we would want to minimize it. Why do you sprinkle fine powder on the carom board? Figure 12.12. You might have noticed that when a few drops of oil are poured on the hinges of a door, the door moves smoothly. A bicycle and a motor mechanic uses grease between the moving parts of these machines. In all the above cases, we want to reduce friction in order to increase efficiency. Figure 12.12. Powder is sprinkled on the carom board to reduce friction. When oil, grease or graphite is applied between the moving part of a machine, a thin layer is formed there and moving surfaces do not directly rub against each other. Figure 12.13. Interlocking of irregularities is avoided to a great extent. Movement becomes smooth. The substances which reduce friction are called lubricants. In some machines, it may also be advisable to use oil as lubricant. An air cushion between the moving parts is used to reduce friction. Figure 12.13. Action of lubricant. Figure 12.13 depicts action of lubricant. We can see two surfaces and in between there is a coat of a lubricant. Page 152. Bujo wonders, can we reduce friction to zero by polishing surfaces or using large amount of lubricants? Haley is happy to answer. Friction can never be entirely eliminated. No surface is perfectly smooth. Some irregularities are always there. 12.5. Wheels reduce friction. You must have seen attaches and other pieces of luggage fitted with rollers. Even a child can pull such pieces of luggage. Figure 12.14. Why is it so? Let us find out. Figure 12.14. In figure 12.14, we can see a child with a piece of luggage fitted with rollers. Activity 12.4. Take a few pencils which are cylindrical in shape. Place them parallel to each other on a table. Place a thick book over it. Figure 12.15. Now push the book. You observe the pencils rolling as the book moves. Do you feel it easier to move the book in this way than to slide it? Do you think that resistance to the motion of the book has been reduced? Have you seen heavy machinery being moved by placing logs under it? Figure 12.15. Motion of the book on rollers. When one body rolls over the surface of another body, the resistance to its motion is called rolling friction. Rolling reduces friction. It is always easier to roll than to slide a body over another. That is the reason it is convenient to pull luggage fitted with rollers. Can you now understand why the wheel is said to be one of the greatest inventions of mankind? Since the rolling friction is smaller than the sliding friction, sliding is replaced in most machines by rolling by the use of ball bearings. Common examples are the use of ball bearings between hubs and the axles of ceiling fans and bicycles. Figure 12.16. Page 153. Figure 12.16. Ball bearings reduce friction. 12.6. Fluid friction. You know that air is very light and thin, yet it exerts frictional force on objects moving through it. Similarly, water and other liquids exert force of friction when objects move through them. In science, the common name of gases and liquids is fluids. So, we can say that fluids exert force of friction on objects in motion through them. The frictional force exerted by fluids is also called drag. The frictional force of an object in a fluid depends on its speed with respect to the fluid. The frictional force also depends on the shape of the object and the nature of the fluid. It is obvious that when objects move through fluids, they have to overcome friction acting on them. In this process, they lose energy. Efforts are, therefore, made to minimize friction. Where do you think scientists get hints for these special shapes? From nature, of course. Birds and fishes have to move about in fluids all the time. Their bodies must have evolved to shapes which would make them lose less energy in overcoming friction. You read about these shapes in class 6. Look carefully at the shape of an aeroplane, figure 12.17. Do you find any similarity in its shape and that of a bird? In fact, all vehicles are designed to have shapes which reduce fluid friction. Figure 12.17. Figure 12.17 depicts similarity in shapes of an aeroplane and a bird. Page 154. Keywords: ball bearing, drag, fluid friction, friction, interlocking, lubricants, rolling friction, sliding friction, static friction. A riddle for you. In some situations, I oppose the motion. In other situations, I facilitate the motion. But I always oppose the relative motion between two moving surfaces. Put some lubricant and I become small there. Make the moving surfaces rough, I make the movement tough. I may be static, sliding, or rolling. But whenever two surfaces are in motion, I am always there. Tell me who I am. What you have learnt. Friction opposes the relative motion between two surfaces in contact. It acts on both the surfaces. Friction depends on the nature of surfaces in contact. For a given pair of surfaces, friction depends upon the state of smoothness of those surfaces. Friction depends on how hard the two surfaces press together. Static friction comes into play when we try to move an object at rest. Sliding friction comes into play when an object is sliding over another. Sliding friction is smaller than static friction. Friction is important for many of our activities. Friction can be increased by making a surface rough. The sole of the shoes and the tires of the vehicle are treaded to increase friction. Friction is sometimes undesirable. Friction can be reduced by using lubricants. When one body rolls over another body, rolling friction comes into play. Rolling friction is smaller than sliding friction. In many machines, friction is reduced by using ball bearings. Fluid friction can be minimized by giving suitable shapes to bodies moving in fluids. Page 155. First, fill in the blanks. A. Friction opposes the blank between the surfaces in contact with each other. B. Friction depends on the blank of surfaces. C. Friction produces blank. D. Sprinkling of powder on the carom board, blank friction. E. Sliding friction is blank than the static friction. Second, 4 children were asked to arrange forces due to rolling, static and sliding frictions in a decreasing order. Their arrangements are given below. Choose the correct arrangement. A. Rolling, static, sliding. B. Rolling, sliding, static. C. Static, sliding, rolling. D. Sliding, static, rolling. Third, Elida runs her toy car on dry marble floor. Wet marble floor, newspaper and towel spread on the floor. The force of friction acting on the car on different surfaces in increasing order will be A. Wet marble floor, dry marble floor, newspaper and towel. B. Newspaper, towel, dry marble floor, wet marble floor. C. Towel, newspaper, dry marble floor, wet marble floor. D. Wet marble floor, dry marble floor, towel, newspaper. Fourth, suppose your writing desk is tilted a little. A book kept on it starts sliding down. Show the direction of frictional force acting on it. Fifth, you spill a bucket of soapy water on a marble floor accidentally. Would it make it easier or more difficult for you to walk on the floor? Why? Sixth, explain why sportsmen use shoes with spikes. Seventh, Iqbal has to push a lighter box and Seema has to push a similar heavier box on the same floor. Who will have to apply a larger force and why? Eighth, explain why sliding friction is less than static friction. Ninth, give examples to show that friction is both a friend and a foe. 10th, explain why objects moving in fluids must have special shapes. Page 156. Extended learning. Activities and projects. 1. What role does friction play in the sport of your choice? Collect some pictures of that sport in action where friction is either supporting it or opposing it. Display these pictures with proper captions on the bulletin board of your classroom. 2. Imagine that friction suddenly vanishes. How would life be affected? List 10 such situations. 3. Visit a shop which sells sports shoes. Observe the soles of shoes meant for various sports. Describe your observations. 4. A toy to play with. Take an empty matchbox. Take out its tray. Cut a used refill of a ball pen of the same width as the tray as shown in the figure below. Fix the refill with 2 pins on the top of the tray as shown in figure 12.18. Make 2 holes on the opposite sides of the tray. Make sure that the holes are large enough to allow a thread to pass through them easily. Take a thread about a meter long and pass it through the holes as shown. Fix beads at the 2 ends of the thread so that it does not come out. Insert the tray in the outer cover of the matchbox. Suspend the matchbox by the thread. Leave the thread loose. The matchbox will start falling down due to gravity. Tighten the thread now and observe what happens. Explain your observation. Can you relate it to friction? Figure 12.18 has 4 images to explain what we just discussed. You can read more on the related topic on the following websites: http:// www.school-for-champions.com/science/friction.htm hyphen-astr.gsu.edu/hbac/firct numeric 2.html. Chapter 12 ends here.